Hi, this is Group 1. We are focusing on the production of the Panasonic Lumix DMC GX7 camera. The camera housing is produced using die casting, a process that produces parts like those shown here. During die casting, molten metal is injected into reusable tools, like these, under high temperature and pressure. The tool, known as a die, is comprised of two or more steel molds that clamp tightly together during metal injection. One of the molds is fixed, while the other moves to access the part upon cooling. After Panasonic sends its housing design to a manufacturer, die development will likely take 1 to 3 months. Once the tool is fabricated, the housing is ready for production. Die casting the housing is divided into 5 steps. The first step is clamping. The two die halves are lubricated and then firmly closed together. The second step is injection. Molten metal is then transferred into the die. The third step is cooling. The die should not be opened until full cooling time has elapsed. The fourth step is ejection. The die halves are separated and ejector pins push the casting out of the die cavity, where the part is then taken to undergo the final step and subsequent operations such as polishing. The final step is trimming. Excess material is removed from the housing. One cycle could take anywhere from a few seconds to a minute depending on part size and complexity. The two main types of die casting differ in their injection mechanisms. During hot chamber die casting, the injection mechanism is immersed in molten metal in an adjacent furnace. This process is best for low melting point alloys like zinc. However, recent technology improvements now permit magnesium alloys to be used in hot chamber die casting. In cold chamber die casting, the injection plunger and cylinder are not submerged in molten metal. A ladle delivers molten metal to the injector, also known as a shot sleeve, in an effort to minimize machine exposure to the hot material. This process is slower than hot chamber die casting and is best for higher melting point metals such as aluminum and copper alloys. Since the dies are made of steel, steel cannot be used in die casting. The camera housing is made of magnesium and was likely produced using hot chamber die casting due to its quicker cycle times. Since each part needs its own custom die, tooling cost is expensive and will likely increase with complexity. Based on online estimates, the tooling cost for the camera housing is roughly $40,000, but considering about 24.3 million digital cameras were sold by Japanese camera companies in 2016, an easily repeatable manufacturing process like die casting is preferable for Panasonic. One major benefit to die casting is the ability to form very complex geometries. However, there are still some limitation guidelines that should be taken into consideration. Uniform wall thickness is recommended, but not required, to ensure even distribution of molten metal. Sharp corners should be avoided and all surfaces should be drafted. For magnesium die casting, the suggested draft angles are 0.75 degrees for walls and 1.5 degrees for inside cores. External undercuts should be minimized as they require extra side cores, which add to tooling cost. Internal undercuts that require lifters should be avoided if possible or redesigned with slots. Standard design tolerances are quite small for die casting, showing that this is a very accurate manufacturing process. Design specs are often validated with X-ray technology. Die casting is a great manufacturing method for high-volume production of intricate parts, often considered the shortest distance between raw material and finished product. Its fast cycle time and impressive accuracy make it a smart production option for Panasonic. Panasonic's selection of magnesium ensures that the camera body is light, yet strong enough to protect internal components. Many internal components of the camera are produced using progressive metal stamping, a manufacturing method that performs a series of processes on sheet metal that is fed at a constant rate. Progressive metal stamping requires material stock, a die split into male and female halves, and a stamping press. As material is fed, the stamping press will perform a specific operation on that portion of the material and then move it to a downstream portion of the die, where further operations are performed. Progressive stamping can contain up to 20 different procedures in a single die. Stamping operations are usually split into two categories, forming and cutting. Forming is the process of bending or displacing material without breaking off, while cutting is the use of shear forces to break pieces off of the main sheet. One particular part of the camera that is progressive stamped is the connector terminal, shown here. Panasonic's first step in producing this part is to design a die, which usually takes a few weeks to fabricate. Once the die is ready, it will be adhered to a stamping press, and the sheet metal will be fed in. The material likely goes through the following operations during progressive metal stamping. First is the punching of dimension holes. Punching is a process of material removal and separation using high shear forces. The shear profile depends on the sheet's metal hardness. Harder materials will shear earlier in the punching process, while softer materials shear after the punch travels nearly full depth. Blanking is a common cutting procedure where the perimeter of the part is cut. There are other more complex types of cutting, shown here, that are not seen in the terminal connector, but are common in other stamp parts. The two fins are bent in a curved channel. Bending can result in an A, V, or other more complex shapes as seen here. A few sections of the rear portion of the terminal are drawn. Drawing conforms the sheet to the die via a punching action without breaking any material off. Progressive stamping is one of the many different types of stamping available. Some stamping dies are capable of performing multiple options in a single step, known as compound dies. Other stamping machines will only perform a single process, but automated systems will transport the material to another machine for further operations, better known as transfer die operations. Similar to die casting, progressive metal stamping has a large tooling cost and requires significant lead time. But since sheet metal is relatively inexpensive and stamping presses can fit almost any die, stamping becomes a cheap option for medium to large production volumes. Similar to die casting, careful consideration must go into die design in order to ensure that parts are made as intended. Hole punching and cutting require specific clearances between the punch and die. Additionally, bending angles greater than 90 degrees should be avoided if possible. Stamped parts inherently must be uniform in thickness and are rarely thicker than 1/2 inch. General design tolerances are usually 1/100th of an inch, but can be as small as 2/1000th of an inch in some instances. Angular tolerance of plus or minus 1 degree is common for formed features. Besides cost, one key benefit to progressive metal stamping is the range of material options available. Aluminum, copper, zinc, and stainless steel are some of the metals used by companies offering metal stampings. The parts in the camera are most likely aluminum or stainless steel. Progressive metal stamping allows for fast and easy production of uniformly thin parts while minimizing necessary labor.